Okay, so in this video, we're going to be looking at doing some line integral calculations with Green's theorem. Now, Green's theorem is typically used to evaluate these differential forms of line integrals, and we're going to convert this differential form with our two functions, mxy dx plus nxy dy, into this area integral where the function we're integrating is the partial derivative of n with respect to x minus the partial derivative of m with respect to y. So let's look at some particular examples. So here we're going to use Green's theorem to evaluate this integral on the path along the boundary of the region between the graphs of y equals x squared minus 2x. So always it's a good idea to orient yourself and sketch the graphs. So this is our line y equals x, and this is our line x squared minus 2x. And so basically what we're doing is since we're going along the boundary, we would essentially be going along this curve here. And then when we get back to the second point of intersection, we would come back along the curve to the origin. Now, if you were to try to parameterize this, you would need, as in our previous example, you would need to parameterize from the previous video, you would need to parameterize this in two segments. So you would parameterize the x squared curve, you would let x equal t, and then the y component would be x squared minus 2 a t squared minus 2t, and then you would do that from 0 to this point of intersection, which looks like t equals 3, and then you would parameterize the line segment back from, it looks like maybe 3, 3, all the way back to the origin. And then you would do that in two segments, and again, substituting into that differential form, similar to the example we did at the end of the general line integrals video. Now, in this case, we're not going to do that. This is a closed curve, and so we're going to take advantage of Green's theorem to do this evaluation. So the first thing that we're going to calculate is the partial derivative of n with respect to x and the partial derivative of m with respect to y. And if we go back to that function, the derivative of this with respect to n, this is n, the derivative with respect to x is that 2. The derivative here with respect to y is 1. So I try to remember this as basically if you already have a dx, this is the function, you do the opposite derivative. So you would need the derivative for y here because it's multiplied by dx. And here you're multiplying by dy. So Green's theorem would need you to take the other derivative, the derivative for x. And so when you do that subtraction, 2 minus 1 is 1. And so basically you're just calculating the area of this region. Now, of course, you could end up with actual functions, but then you would still integrate it over the region. And so we're going to set up our area for our double integral. The bottom limit is the squared function. The top limit is the x function. And then we're integrating in the x direction from 0 to 3. And then the antiderivative of 1 is y. We plug in our two functions, the area bounded between the two curves, and then we integrate that from 0 to 3, and we end up with, in this case, 9 over 2. Now, again, you can parameterize this, but you should end up with the same answer. And the parameterization, because you have to do it in two parts, does take a bit more calculating. Now, Green's theorem also can really help us out in weird regions or when our functions are particularly bizarre. That's often one of sort of the hints of a textbook problem where they're expecting you to use Green's theorem. And so they give you these crazy functions, but you would not want to integrate this by parameterization. Putting trig functions inside of an exponential function would be horrifying. But on the other hand, when you use Green's theorem, this is our multiplied by dy, so we take the derivative for x, and we get a nice 1. And this one is our multiplied by dx, so we take the derivative for y, the exponential goes away and we get -1. So, so using Green's theorem will make this ugly integral much easier to do. Now, we also want to do this along the path of the boundary of the region lying between the two graphs of the circle of radius 6 cosine theta, 6 sine theta, and the ellipse, 3 cosine theta, 2 sine theta. So this is our graph. Again, it's outer circle, inner ellipse. Now, if we were to try to parameterize this and do it piece by piece, because we have two completely different sections, technically what we would have to do is we would try to create a path where we're following along the boundary, where we're always, the area of the region that we're looking at is always essentially to our left. So this outer curve we would parameterize as going counterclockwise. And then what we would do is we would have to create a path that goes from the outer boundary to the inner boundary. And then we would have to go clockwise around the inner boundary, again, in order to keep the region to our left. And then when we came back to this point again, we would go back along the path to the outer boundary to close that boundary. Now, the advantage here is that the segment connecting the outer to the inner boundary and then the inner boundary to the outer boundary are exactly negatives of each other, and so they will cancel out. But if you had to parameterize this as a closed curve, then that is effectively what you would have to do. That would be 4 segments of parameterization. And even if you consider that the sort of connecting pieces will cancel, that's still a lot of extra work. Not only in the parameterization and getting the orientation correct, but then in doing the integration. If we can do this as a double integral of an area, that would be even better. Now, let's go ahead and calculate the function we would need to integrate for the area. And so as I mentioned, our end function, we're going to take the derivative for x, and the crazy y term cancels out. We just get 1. And same thing for our m term. We take the derivative for y, and our crazy x component cancels out, and we get this. And so the difference between them is just 2. And that's 2 times the area. Now, integrating this in polar coordinates is not really going to be fun. The inner boundary isn't that bad because the outer boundary is just r equals 6. But the inner boundary is actually an ellipse that is quite nasty to try to integrate, and I'm not even going to attempt it. But since this is 2 times the area, according to our integral, that we can actually just find the area by using geometry formulas. So for the circle, we know that the area of the circle is pi r squared. And since the radius of our circle is 36, this radius of our circle is 6, the area is 36 pi. Now, the formula for the area of an ellipse is the semi-minor axis times the semi-major axis times pi, so AB pi. So in our example, that would be 3 times 2 times pi, or 6 pi, for the area of that ellipse. And so the area of that inner region bounded between the two curves is just the difference between these two areas. 36 pi minus 6 pi is 30 pi. And then for the whole line integral, since that's twice the area, we would multiply by 2 to get 60 pi for the whole thing, for the area of our line integral. And again, as long as this is a constant, you can do this trick. If you know the areas of the circles or things like that, you can just calculate the area by other means rather than doing the integration. And in fact, this problem is the kind of thing that a textbook would only give you if they knew there was a workaround to doing that nasty integral with this cosine in the denominator. Now, there are other notations for Green's theorem that you will sometimes see floating around. Again, in different contexts, we will see slightly different things, but there are other versions of them. We will deal with Stokes' theorem in the next video, but that will extend Green's theorem to 3 dimensions, and we'll consider that later. But again, you'll see this curl function is sometimes used here. Part of that is because in 2 dimensions, the curl is just the k component if you have only things in x and y. And then if this is not 0, that's the only thing that survives because the rest of the curl will be 0 if you're in 2 dimensions. And so you'll see this notation that is equivalent to this. And here the k vector is, you're basically dotting it with 0, 0, 1, which is why, again, only the k component survives. The theorem can also be written with a vector that is normal to the surface, which is f dot nds, which is the divergence of f. And again, you get something that looks somewhat similar. Their analog to this is the divergence theorem, which is a surface integral problem, and we'll deal with that again in a completely different video. But you will sometimes see this notation. Application of calculating the area bounded by a line integral. Calculating the area using a line integral will sometimes give you this formula, where the area is 1/2 y dx plus x dy, using the boundary of the region in question as the path. So you will sometimes see those kinds of calculations, area as a line integral, and these ones are typically readily evaluated using Green's theorem, or the functions are simple enough, you may be able to do it in terms of just the definition. All right, so we're going to stop here, and then we'll continue on in the next video with Stokes' theorem.